Now, we talked in the last screencast about how alkanes can form normal chains, which we consider to be all connected, and they can also form branched chains. But it turns out that alkanes can also form rings, and when they form rings, they're called cycloalkanes. Like kind of all the other alkanes, cycloalkanes are not found in human cells. However, we have several important molecules in human cells that do contain rings of 5 or 6 atoms. And so the study of these cycloalkanes is going to help you better understand the chemical behavior of these complex molecules. Now, when we look at these cycloalkanes, we need to remember that the carbons are what are bonded to each other. All right, and we end up with a condensed formula that looks like this. And this is really that skeletal formula that we were talking about. And so you can see how here we know there's a carbon, and it's just understood there are 2 hydrogens that are attached to that carbon. And so one of the things I want you to notice here is if there is a cyclic molecule, you do now use a cyclo prefix in front of it. So let's practice, let's look at how we name cyclic molecules. So if you just have one group, if there is just one substituent, on a ring, the substituent has no number. Because remember, this is a 3-dimensional structure, and no matter which way you turn the CH3, it's only gonna be in one place, right? And so we would just call this methyl cyclopentane. Now, once you have more than one substituents, then you have to number those. So if there is more than one substituent, you need to number these substituents. And remember that number is telling us the location. That's sometimes called a locant number. And so we need to give the location. Now, as you're numbering, you need to remember that you want to end up with the lowest numbers. So for example, if we looked at this molecule, we would number it 1, 2. We would not number it 1, 2, 3, 4, 5. Okay, so it would be 1, 2 dimethyl cyclopentane, not 1, 5. Same thing here. When we look at this, we've got 1, 2, 3. This would be 1 chloro 3 methyl. Now, it would not be 1 chloro 4 methyl, and it would not be 3 chloro 1 methyl, because if we started here 1, 2, 3, that would be an example where we had a tie, where we had a 1 and a 3 no matter what we did. And so we need the 1 then to go with the lowest alphabetically, right, or the first alphabetically. And so this is how we name cycloalkanes. So let's do an example. So it says represent the following cycloalkanes by a geometric figure and name the compounds. So when we look at this, there's 1, 2, 3, 4, 5 carbons here in the ring, and then this CH3 is off the ring. So when we look at the geometric compounds, right, it's like that, and then we would put one off the ring there. Then, because there's only one substituent, we don't need a number, we would say this is methyl cyclo, because it's a circle, it makes a ring, and it's a 5-membered ring, so we would say that's pentane, and the A and E ending there is all single bonds. Now, we come over here and we look at this structure, and there's 1, 2, 3, 4, 5, 6 carbons there, and so that's going to form a 6-membered ring. It looks like that. And then we are going to end up putting a CH3 here, right? And I drew that CH3 in, but let me back that up there and just draw the line. And then we are also going to then also put a CH3 right here. So now we have two CH3s, and they're 1, 2, 3. That's the positioning there. And so we would name this then 1,3-dimethyl cyclohexane. Now I want to point out that between numbers, you need to use a comma. And then between a number and a letter, use a dash. Okay, and we saw that in the previous screencast as well. And so this is how we can go from or write these skeletal structures and then name them as well. Now, remember from a previous screencast that we talked about carbons give us a tetrahedral orientation. And bond angles of 109.5 is really characteristic of carbon atoms that form 4 single bonds. In certain alkanes, however, a tetrahedral arrangement for the carbon-carbon bonds isn't possible. So, for example, when we look at the bond angles in cyclopropane here, they're really about 60 degrees. And so that's very strained. And what we say is that's got a lot of ring strain and it's very unstable. Okay. When we look at cyclobutane, those have bond angles that are close to 90 degrees, which again is still far away from that 109.5. Now, however, cyclobutane will bend slightly from a planar structure and it'll reduce the crowding. And so this will bend to reduce crowding, right? And cyclopentane will as well. Now, let's talk about cyclohexane for a moment. When we talk about cyclohexane, the bonds here can be arranged in such a way that the carbon atoms can be tetrahedrally arranged as long as everything doesn't lie in the same plane. And so what this means is it takes kind of a puckered shape, and these puckered shapes are called either chair or boat. And so I'm going to show these to you in class because I don't feel like this is a really great representation of the chair here, but if you were to kind of imagine it, it's kind of like a lounge chair where here's kind of the body there, and then the top part of the chair comes up here, and then the bottom part of the chair comes down there, right? And so you would kind of lounge by the pool on a lounge chair, and so that's where that chair comes from. And then boat, you go up, over, and up, and so it kind of looks like a boat here. And so these are the two arrangements. But in this arrangement, these bond angles are very close to that 109.5, right? And so that means that it's quite stable. And in biology, and when we get to the biochemistry part of this, we're going to see that a lot of the rings that we find in our body are kind of these 6-membered and 5-membered rings because they get really close to that bond angle. Now, I want to remind you that free rotation can take place around single bonds and alkanes, okay? And that's what we mentioned before, that these guys can rotate around. But there is no free rotation that's possible in the ring structure because, right, the carbons are really held in a fixed structure. So, and if you broke those bonds, it would require a really large amount of energy. So that means if we've got groups that are on a certain side of the ring, they're not going to rotate around. So what do I mean by this? Well, if we look here, and so this is drawn to kind of help you imagine this in 3D. Basically, these carbons are coming out towards the front and these carbons are in the back. And if you have two CH3s that are attached here, they're below the ring. But you can also have a CH3 that's above the ring and below the ring. And so when the CH3s are on the same side, they're referred to as cis. And when they're on different sides, they're referred to as trans. These are completely different molecules with different molecular properties. So the way I remember this is I like alliteration. So cis, same side. And so these are on the same side. And then trans are on opposite sides. Now, this leads us to kind of an important point, which is called stereoisomerism. And so we've already talked about some isomers, and now we're introducing stereoisomers. And these are just compounds with the same structural formula, but different arrangements of atoms. Okay. And we can also have geometric isomers, and those are those cis-trans isomers. And so I want you to remember that cis means the groups are on the same side. And then trans means the groups are on opposite sides. Now, let's look at an example like you would see a question for example in the homework. So we need to name and draw the structural formulas for all the isomers of dimethylcyclobutane. Indicate which ones are geometric isomers. So when we think about dimethylcyclobutane, and if I was to kind of draw this kind of in the same fashion, where I'm saying, hey, look, this is coming out towards us right here, okay? We could put the two CH3 groups on the same carbon here, and that would be, right, a 1,1-dimethylcyclobutane. We can also put these two groups, right, on two different carbons, and one can be above and below the ring. And so, for example, this would be trans 1,2-dimethyl cyclobutane. The 1,1-dimethyl, doesn't have a cis or a trans because they're on the same carbon. So if they're on different carbons, that's what we're talking about here. So we have trans 1,2. This means that we can also have cis. So for example, if we come here and this is kind of coming out of the front, we could have two CH3 groups, right? And that would be cis 1,2-dimethyl cyclobutane. And then you could also see, right, a 1,3. So for example, all right, that would be a trans 1,3-dimethyl cyclobutane. And then that would be an example of a cis 1,3-dimethyl cyclobutane. Okay, so those are all the structural formulas in the cis and trans isomers that we would have from butane with two methyl groups on it. So you can see that we've got the spacing where they're both on a 1, then there's a 1-2 spacing, and there's a 1-3 spacing. Now we don't do a 1-4 spacing because that's the same as a 1-2 spacing would be. And then also I want you to notice that I drew both of these up, and then I drew down here both of these down. These are still both cis, because if both of these are up and we flip the ring over, then both of them would be down. And what we're really looking at here for is, are they on the same side? Not necessarily that they're up or that they're down. And so those are just kind of some tricky things. If you're struggling with this, know that you are not alone. Going from 2D to 3D is really, really hard. And I struggled with this as a student, and so I'm happy to help. So as always, if you have questions, please feel free to stop by my office.